Okay. Some pretty cool practical requirements. So if this one says that if there's a car driving towards the ego car in the current frame. So if you have a car approaching, so if I'm into a car, I'm basically performing verification in my surroundings. I'm performing perception in my surroundings. If I see that a car is approaching me, it must exist in the previous frame. And just to give you a diagrammatic view, if this is what we say that if we say that this is closed enough, and if this is the ego car and we are moving, it should basically have a car here. So what it did is it detected the car here, but in the previous frame it never detected the car. So what we want is it should detect the car in the previous frame as well. And how do we define the requirements? We freeze times, we have IDs, and we say what we broadly say if a car exists. So if a car exists and the distance is close, it should have existed before. This is a previous operator. That's why it deals with the weak previous. So what we're saying is if a car exists and the distance to the car is close, it should have existed in the previous frame. And how the predicates are is as follows. So if you just look at car existed, it basically says that there's a car with ID1 and the class is car, and ID3 is basically the drivable area of the road. So this is what says the car exists and the distance is close. Distance is close, this basically translates to this particular box, the one in the green. And this part, the one which says before existed, it basically says that you're checking at the previous frame and you're checking at IDs at the previous frames because there's a weak previous operator. So you're basically saying that in the previous frame, there exists an ID where this ID2 is a car. It matches the ID of ID1, which is the next frame, and the distance to it is basically close, it's within this range. So this is how the entire this requirement with respect to ego car is formulated. And if you want to look into occlusion, this is last example. So what happens here is that what this requirement says is that if there's a car, if I've seen a car and it disappears and it's not near the borders of the frame, borders of the image, so it's likely that it would have been occluded or basically covered by another object. So if there exists a high confidence object and in the next frame it suddenly disappears without being close to the borders, then it just be occluded by another object. That's what we are trying to say. Because again, cars won't disappear with you. The main specification says the same thing. High probability of car being present. It's farther than the borders, so the car is not near the borders, and it disappears in the next frame. So it is occluded, implies occluded. And then you have these particular specifications that follow. I think it should be, I think you get the gist. You say that the probability of ID1 greater than 0.8. So you have a high confidence value. You said that the borders are far away. So this basically says that it is somewhere in the middle of the frame, not very near to the borders of the image. And it disappears so that ID no longer exists. What it means is occluded. Now, how did they define occluded? They say that there's an object which disappears and the object which makes it disappear. So they give ID3 to the one that disappears, ID4 to the one that makes it disappear, and then you have this entire requirement which says that, hey, it's covered. And these are the main 5 examples that I wanted to give in order to motivate how STPL works. And if we have time, we can either take up some questions.
So I have a question regarding, so for example, now supposing we train a perception model, it has an accuracy of 99.97%, but in that, it does not detect a person at all. So this would not work in that case, right?
True. That works.
Okay. And the second thing is that supposing we have an environment which is unfamiliar. So, for example, in case of driving a car, we have black ice. So, in case of black ice, if you press the brakes, you start skidding. The car will start skidding.
Okay.
So, in that case, even if we define this, it could be possible that someone has not thought about these conditions, and in that case, even though we are satisfying all our metrics, it would still fail.
That's true. So for the first point, that is basically an issue of the perception model.
Yeah.
If you have a ground truth data and you're detecting a certain object throughout the sequence, there's an issue with the perception model. That's the first one. In the second one, these logics do not take into account erratic behaviors, at least for now.
I have a question. So, like in one of the previous lectures, where we learned the neural ASP stuff, like there's logic that identify whether this car perceived by the perception system is a toy car or a real car, is the spatial relation between the car and the person. I wonder if you remember that. That kind of because I don't have experience in doing computer vision projects, like this seems like it's based on pure computer vision systems, but somehow it can detect the longitude and latitude, which is spatial stuff.
Yeah, so by lat and long, they do not mean in depth. So they can have, to shoot the word. So in terms of lat and long, they deal with a 2D frame. They do not deal with depth inside the image. So they don't take depth, how far another car is from you.
Okay.
They do not consider that currently in this STPL language.
Okay.
But they do have these latitudes and longitudes. So latitudes and longitudes, basically lat long basically means this. They are basically defining distance from all of the four sides. It just helps you write things in terms of distance.
I was thinking this is a bird eye view where the car is.
No, it's not currently. But that is something that would be an extension. Because
that would be just a spatial topography.
Yeah. So it would just be added something in the spatial part of the capital term.
I have a question in the last slide. So in that, what if we have an occluded object's bounding box is less than the non-occluded object's bounding box?
It's just a confidence value they put according to their experience. So you could make a more complex requirement where you have certain conditions over how do you say that the probability of range of a car is high. So these are like very, very basic, just for the paper. You can always have complex requirements that capture what you need. If that answers your question.
They do the experiment or provide implementation here or offer any data?
Yes. So there are some results on how the time looks like. What I want you to take away from here is that the sum of these basically tell you the number of operators inside a particular formula. And these are basically the memory complexities and then the time complexities. So there's not a lot that I can comment about here because in a way this is novel, so they have no way of comparing it to a certain benchmark. But they do have code base available for this. And there are multiple monitors as well. So I can send you the link after the class if you're interested.
Actually, could you send the link to the code to Lahari and she can post it on Canvas for the class?
I have another question. Sorry. So because this is a metric, I assume that it should be tested on a model instead of a data set. But why we're saying that?
Well, so these basically say that if I have a very complex requirement, how much time does it take to evaluate that particular requirement?
Okay.
So it's complexity in terms of how does my computation time and memory space, the space time grows in correspondence to the number of variables, the freeze time operators, the operators, temporal operators inside a particular logic.
They used a model on that data set.
Yeah. So if I'm not wrong, they basically use something called the squeeze deck, which was introduced for the purpose of autonomous driving, and then they tested it on Berkeley deep dive data sets. And if you're interested in knowing more, these 8, 9, 13, 14, 15, again, these are the requirement numbers, and then you can like go ahead and map them if you're interested.
And as a side note, like in certain logics, checking entailment of a sentence, which is what a specification is, can sometimes be very costly. And the point they're trying to make is that this can be done efficiently.
And then we are done with the presentation. If there are any more questions, I can take them now. Or there's something that I think you mentioned about how do we evaluate, how do we monitor robustness, the quantitative values. I'll get into that. So actually, can you pull up the slide of the automatic translation? So what I want you to see is if we have this area and we have this particular we have this certain robot and it's following a set of dynamics. We give it an initial point, we know the internal dynamics about how it would operate internally, and then you have some continuous states here, and then it just basically keeps on moving, so it follows a certain path. Let's say it starts from here, and this is a set we want to avoid. So what you would do is you would simulate the system, and then let's say this is one of the paths which is followed, and let's say this is one of the paths which is followed. So just one quick inspection, this one has falsified because we do not want to enter this space, while this one has not falsified. How the requirement would look like is always 0 to t. Let's say not box. We do not enter that box. What the always operator would do is, it's basic. If you think about it, it's basically an AND over multiple times. And in order to show how robust or how satisfied or how violated it is, what they do is they define a distance, which basically says that how far was this trajectory from the set. So in this case, it would basically be a signed distance of this value. And since you're looking at operator always, you basically take the min. So here you would have some positive value, here you would have some positive values, and then you would start having negative values here because you're inside the set. And then again, you're looking at positive values. So what the always operator would do is it would take the minimum of this value so that it gets one certain value. So it would take a minimum over this entire trace. And then it will take the minimum value. So if the minimum value is less than 0, it has violated the specification. If you look at the one here, it basically never enters. So the most minimum value would still be positive. That's why the degree of satisfaction is it's positive. The robustness is positive. And then just like this, it's alternative. The eventually is basically a max because it's like an OR. So what OR says is if you have an OR condition or you have a disjunction of multiple conditions, even if one of them is true, the entire statement is true. So for it to be false, everything has to be false. So you take a max of how far everything is. And if that max is greater than 0, you basically have satisfied the requirement. So that's how the computation takes place in STL. And it's far more complex in STPL. So this is just the example I will give.
So you mentioned that there were more related works like TPTL, standalone STL. Did they happen to like compare the big O or the relations?
But so this is completely in STPL. There's no STL in this particular paper.
You mentioned something called TP.
Yeah, so those were extensions of so TPTL basically deals with if I'm not wrong, it basically deals with timed operators in perception. So it deals in the free. So that this work basically introduced how to freeze times, how to freeze frames, and how to deal with that kind of logic. What S4U does is it deals with stuff in the spatial framework. So the areas, the bounding boxes, how the topology looks like. what this particular paper does, the STPL is, it is an intersect, it is basically an extension of both of these languages. So it basically has the best of both of these and it is an extension over that as well.
Yeah, but to prove the robustness, they might wanna see like the bigger notation that
Uh,
space or time compared.
They do not compare it with any other paper, but they have bigger notations for their own language.